Hi guys, welcome back to my channel. Today we're going to be looking at some applications of first order differential equations. So a first order differential equation is always useful when the growth rate is proportional to the current value. And that doesn't really matter what the topic is, only that is the case. So I could apply this to something like a population of rabbits, or I could apply this to something like the cost of a house, where the rate of growth of that house is proportional to the current value of that house. And we could also apply this to things like businesses, where they have some level of growth that's proportional to the growth in their current business. So I'm just going to go through a few different examples here, but I don't want you to think that these are the only applications of first order differentials. So the price of houses in a certain area grows at a rate proportional to the current value. So in other words, let's start defining some terms here. So if we say that P is equal to the price, and that's going to be in dollars, then we have T, which is going to be time. And in this case, let's have a look here. They're saying in 2018, and what was the value of the house in 2010? Based off that scale, I think I might use time in years. Okay, so we have dP dt is going to be proportional to the current price, and therefore dP dt is going to be equal to kp. When we go ahead and we integrate these sides, we end up with P is equal to P naught e to the power of kt. So let's put some values in here. So in 2002, the house was purchased for $315,000. In 2018, the house was sold for $1,260,000. What was the value of the house in 2010? Okay, so let's define this as our time 0, so when t is equal to 0, and therefore this is going to be when t is equal to 16. So we can substitute these values in. We know that when t is equal to 0, this is going to be e to the power of 0, so therefore p naught is going to be equal to 315k. So P is equal to 315,000 times by e to the power of kt. Now we can use this information here, and we can substitute that into our equation to determine our value for k. So 1,260,000 is going to be equal to 315,000 e to the kt. So dividing both sides through, we get 4 is equal to e to the power of kt. So if I take the natural log of both sides, I'm going to end up with kt. Oh, and what I've forgotten to do, I've forgotten to substitute 16 in here. So this should be k times by 16. So I can go ahead and I can divide both sides by 16 to get my value for k. Now, this is probably going to be a decimal answer, so I'm going to leave it in this exact form, and I'm going to substitute that back into my equation to solve for the value of the house in 2010. So here we have our formula. So last thing we're going to do, we know that in 2010 that t was equal to 8 because that's 8 years after 2002. So now I can just substitute that in. So we have 315,000 times by e to the power of ln 4 over 16 times by 8. So let's chuck that in our calculator. So for our solution, we get 630,000. And that seems pretty reasonable to me, given that in 2002, it was about 315,000. And then in 2018, it was about $1 million. So 630,000 does sit in between those values, as 2010 sits in between those values. And so this does seem like a reasonable response. Let's have a go at another example. The elimination time for alcohol, so the time it takes a person's body to remove alcohol from their bloodstream, is measured as T is equal to 1 over K. The process varies from person to person, and so the value of K will vary. For one person, the elimination time is 3 hours. For this person, how long will it take the excess level of alcohol in their bloodstream to reduce from 0.1% to the legal adult driving level of 0.049%? So this doesn't necessarily sound like a application of a first order differential equation, but if we say that, let's say A is the volume of alcohol in the body, and we have T is the amount of time in hours that it takes to remove that, and this volume, by the way, is as a percentage, then the change in the percentage of alcohol in your body over time is proportional to the current percentage of alcohol in your body. And so this is indeed a first order differential equation. So given some information now, we know that for one person, T is equal to 1 over K, and that's equal to 3 hours. And so if we rearrange this, we're going to get 1 is equal to 3K, and so 1 over 3 is going to be equal to our value for K. The other piece of information that we know is they have this much alcohol already in their bloodstream. So let's rewrite this formula so that we have A is equal to 0.1 e to the power of 1 over 3t. Okay, so let's go ahead now and let's use this formula to answer this question. How long will it take the excess level of blood in their bloodstream to be reduced to this value here, or less than 0.05. Just in case you guys didn't know that, I didn't know that, but when I was watching RBT the other day, there was some guy and he literally was 0.5, so like 0.05, and so he was like, oh, excellent, like, you know, I've met the criteria, I'm under the limit, everything's all gravy. But they said, no, you have to be under 0.05. So because you're exactly on 0.05, we can still charge you. And so he had to get taken back to the station and they had to do a secondary breath analysis. So just so you guys are aware, when you guys go and get your full licenses and you start drinking and driving for the first time, for smaller people, so they often say that for females, you should have 1 drink per hour, but in reality, if you're a smaller male as well, like I wouldn't have any more than that. So just as an aside, there's something that you should be aware of when you go out into the world. So let's go ahead and let's solve this problem. And I've just realized I made a little mistake here. This is decreasing the amount of alcohol in the body. So this rate should be a negative rate. All right, so let's substitute in 0.049 is equal to 0.1 e to the negative 1 over 3t. So now we just need to go ahead and rearrange and solve for t. So this solution for the time is 2.14 hours. So there you go. So don't drink and drive or wait 2 or 3 hours before you actually go ahead and drive. All right, guys, that was my little rant for today. So that's how we use some first order differential equations to solve rate problems. See you in the next video.